What do airplanes, cars, and health monitoring systems all have in common? They all form a group of what's called safety-critical systems, that is, systems whose failure may result in injury or loss of life.
There are also fields where artificial intelligence is being developed to reduce human error. Some examples of implementations in the industry include autonomous driving as well as robotics.
More complicated AI systems are like black boxes. We have an input, we have a function model, and we have an output. However, we're still uncertain of the workings of our actual model, and that makes it difficult to guarantee what our output looks like. So under safety-critical settings, what guarantee do we have that our AI actually does what it should? A lot of existing studies make use of the PAC framework of learning. This stands for probably, approximately, correct. And this means that with 1 minus delta confidence, our model will have learnt the target concept with a 1 minus epsilon error of approximation. Hence the name probably approximately correct. Linking this back to safety-critical systems, safety-critical systems with a guarantee need to be able to identify auto-distribution scenarios which might hinder performance or result in injury. So, in the instance of an autonomous vehicle, the following situation might be considered within distribution, that is, expected, whereas a situation involving, for example, a car on fire would definitely be considered auto-distribution. And while this may not be included within the training library, this still has to be recognized with a certain level of guarantee. Assuming we have a training set of in-distribution images, this project aims to train variational autoencoders to replicate the properties of the in-distribution images within a Latin space encoding, that is, representing higher dimensional inputs as lower dimensional inputs. The Latin encoding allows us to distinguish numerically between in-distribution and auto-distribution samples. So, taking a look at auto-distribution sample encodings, we might find that they lie outside the clusters that would be created by within distribution samples, and thereby they can be easily identified and isolated, and safety-critical systems are able to. The hardest part of this process is creating safety barriers to distinguish between in-distribution and auto-distribution samples. Assuming we have a handful of in-distribution samples that have been encoded into the Latin space, we can attempt to create safety barriers using kernel density estimators to create a probability distribution within the Latin space. By comparing this with the encoding of future samples, we can then establish to a certain level of significance whether that sample is within distribution or out of distribution depending on its conformity with the existing set. The number of violations encountered can be then used to calculate the actual error that our model has with a certain level of confidence.